Good afternoon, everybody. Welcome to a wonderful Monday afternoon of Chem 170 with your host, me, Dr. White. Hope you all had a good time since we last met. I've been busy. One thing I should point out, I didn't have a chance today, but tomorrow I will. The lab you handed in last week, I've graded. I'll upload sometime tomorrow your lab scores into D2L. Now, important thing, remember, on this Wednesday, I will be giving test number 1. And let's go to D2L. All right, thumbs up, people. Everybody see D2L? Thank you, Ignacio. All right. Remember, and I posted this last week, but let's go over it again. This Wednesday, I will give test number 1, and it has 10 pages, 14 problems. Some of the problems have multiple parts. I have never and never will in Chem 170 use a multiple choice question. It'll cover alkanes. I should have put down there cycloalkanes also, or I could have just put down hydrocarbons, alkenes, double bonds, alkynes, triple bonds, and aromatic compounds like benzene or toluene. And the points breakdown, 13 points general knowledge, 45 points nomenclature, 47 points reactions. You notice it adds up to 105 because there's five big bonus points. Now, I don't have a problem that I say this is the bonus problem. No, I just have the test add up to 105. You pick what you want to be the bonus problem. Not really. I grade the whole thing. But if you get everything right, you get 105 points. Now, let's go through general knowledge things everybody should know, like how many bonds to carbon, other things. Nomenclature. There's 2 main types of nomenclature problem. One is, here is the structure. What is the Iupath name? The other nomenclature type problem is, here's the name, draw the structure. And finally, reactions. Reactions will be all but one, give the product or products for the following, or organic products. The one exception will be give the starting materials for this reaction. And we've gone through all that. Every problem on my test, I've gone through the concept behind that problem at least twice, usually a lot more. Now, here's how it's going to work. Sometime on Wednesday, and I might even do it right before Wednesday's Zoom meeting, I will send out a password for the password protected PDF file of test number 1 that you'll get from the assignment area of Blackboard, just like where you get your labs. And you'll have from the Wednesday, from the time I send it out, which probably might even be around noon, until the next day, which would be the 22nd, which is a Thursday, 11 a.m. to take test number 1 and upload it as a single PDF file to D2L. Now, let's do this. First of all, let me go to student view. If we look at assignments, you'll already see test number 1 is there, but it's not open. Tomorrow at 9 a.m. it will be open for you to download the file, but it's going to be password protected, and you'll have to wait until Wednesday when I send you the email with the password. You put in the password, and you can take test number 1. And now I'm looking at it in my view. When it is open, nope, I can't do that. All right, but anyways, When it is open, you'll see, let's see if I can try something else my way to show you. You'll see test number 1, PDF file, instructions how to take it. Same thing what you're doing with the labs. And then if you want, if you don't have your own scanner, you can use Cam Scammer. Do not buy the paid version of Cam Scammer. Use the free version if you're going to do that. I also have in here how to take a PDF file, or actually a pictures from your cell phone if you don't have a scanner, and convert it into PDF with Word or what's the Macintosh operating system? I don't know. I don't use Macintosh. I'm not an Apple person. I like apples and apple pie, but not my computers. Ooh, it's awful one Monday humor. Actually, that wasn't too bad. But anyways, that's what you'll do. And let me cancel this. And it'll be visible tomorrow. You can download it, and then you'll get a PDF file, and it'll have the password. All my passwords are always lowercase. I don't play upper lowercase game because students get confused by that. It's just lowercase, letters and numbers, and you put that in there. Now, if you do not have a printer, take a piece of paper, write your name on it. Don't forget to do that. And then for problem 1, put 1 and put your answer. You do not have to copy the problem again. Just write down your answers. Then you make a PDF file you upload either with your scanner, or if you don't have that, with your cell phone, or someone else you know who you can borrow their cell phone. I think nowadays just about everybody your age in this class should have access to a cell phone. Mine's hooked up to a Bluetooth phone right there. I cut my landline a long time ago. All right, any questions about test number 1? I think I cut my landline in, what was it, 2017. I kept it a while. My best friend said, why are you wasting your money on that? I said, well, I can't hear with a regular cell phone. He said, look for Bluetooth. And they have these really nice amplified ones for people who are hard of hearing like me. All right, well, in that case, it's time for the review for test number 1. Everybody see test number 1 review on your screen? Thank you. Now, I shall say this. I try to cover all aspects of things that could be on a test. Once in a while, I might forget something. If I don't have in the review, but I've talked about it at least twice in our lecture meeting, it's fair game. Also, anything in the lab, nothing will ever be on the test from the lab area. I keep those separate. Also, I have test number 1 review as a Word document and a PDF file secretly hidden in the lecture folder D2L under the secret name test number 1 review. So everything you see on the screen right now, you can download. All right, let's go get working. All right, the first thing you should know, definition. What is a hydrocarbon? And that's a molecule with only carbon and hydrogen atoms. Next, there are 2 types of hydrocarbons. One is saturated hydrocarbon, and you should know that definition is a molecule with only carbon and hydrogen atoms, in which all carbon-carbon atoms or carbon-carbon bonds are single bonds. Remember, single bond, 1 pair of electron, double bond, 2 pair, triple bond, 3 pair. That's something you should know. That's general knowledge. I'll say that again. You should know a single bond, 1 pair of electron, double bond, 2 pair, triple bond, 3 pair. And also you should know a pair means 2. Now, saturated hydrocarbon, molecule with only carbon hydrogen atoms, which all carbon-carbon bonds are single bonds. Unsaturated hydrocarbon are molecules with only carbon hydrogen atoms. That's what a hydrocarbon is, but unsaturated tells you they contain one or more carbon-carbon double or triple bond. So saturated carbon-hydrogen atoms, all carbon-carbon bonds are single bonds. Unsaturated hydrocarbons, excuse me, I'm getting all choked up over this stuff. Oh, that was awful. Sorry. But anyways, unsaturated are molecules with only carbon-hydrogen atoms, but contain at least one double bond or triple bond. Now, we talked about the alkanes and the cycloalkanes, and this is wrong. That should be the cyclic, not acyclic. I'll have to change that. But anyways, I won't ask that on a test, but it's good to know. Alkanes are acyclic, meaning not in a ring hydrocarbons, saturated, and cycloalkanes are cyclic, meaning in a ring hydrocarbons. Now, time out for a commercial from Dr. White. Don't forget, when you drive by a gas station, half the weight of gasoline is alkanes, hydrocarbons. If you happen to use a barbecue, the propane, alkanes, hydrocarbons, saturated hydrocarbons, or alkanes. If you happen to use baby oil or Vaseline, took me a second to remember the second thing, those are alkanes, saturated hydrocarbons. And finally, if you light a candle, half the weight of a candle wax is saturated hydrocarbons or alkanes. Remember, it won't hurt you to think about organic chemistry when you're not in my class, because it's everywhere. I stole that from SpongeBob. All right, end of commercial. All right, now, you should know how to draw alkanes and cycloalkanes. And one of your friends on every test and the final, especially test one, there's always 4 bonds to carbon. How many bonds to carbon? 4. 4. See, I'm ambidextrous, I can do it with both hands. You should remember that. And I showed you how to fill in the hydrocarbons. Let's do one real quick. Yeah. And why don't you put in the hydrogens in that molecule? That's all I'm asking you to do. When you're done, give me a thumbs up. And let's wait for everybody to finish. All right, let's get going. Remember, there are 4 bonds to carbon. This carbon has 1 bond. 4 minus 1 equals 3. So there's 3 hydrogens. This carbon, this carbon, this carbon, this one, same thing. Now, let's look at this carbon. 1, 2, 3 bonds. 4 minus 3, because there's always 4 bonds to carbon is 1. So we put 1 hydrogen. Same thing with this carbon. 1, 2, 3. 4 minus 3 is still 1. Well, that's good to know. And finally, this last carbon right here, we have 1, 2, 3, 4 bonds. 4 minus 4 equals 0, which is why I don't have to put hydrogens there. Now, one of the things I saw grading the lab over the weekend, and I'll just do a quick thing. On my test, first of all, this is called the condensed structure. I'll never ask what's a condensed structure, but I will have draw the condensed structure. Now, let's say we had 2 carbons, and I can draw it this way, which is the condensed way. Expanded, which wastes a lot of time, and you don't have to do, I saw some of you do on the lab, which means you're wasting a lot of time. When you show the carbon-hydrogen bonds like here, instead of condensing it like here, yeah, I'll accept that on a test, but you're wasting a lot of time. This is called the expanded structure. I highly recommend you do always the condensed versus the expanded. Do it this way because it saves you time. It's less brain power expended on things you don't have to expend. All right, let's get back to our review. All right, next I asked you to know the Iupath nomenclature rules, how to use them. I'm never going to ask on a test, what's this rule or that, what's that rule? But I will ask you to know how to find the longest chain, how many carbons, pick the right alkane name, like methane through decane, 1 through 10, and then the alkyl groups, methyl, ethyl, N-propyl, isopropyl, N-butyl, tert-butyl. Oh, that reminds me one thing I didn't mention about test number 1. In the letter I'll send you, you are not to look at the internet, you're not to look at your notes, you're not to get help elsewhere. Now, since you're taking it at home, well, how do I stop that? Well, Dr. White's clever, and I've been on Zoom for now over 2 years. It's been that long. And I found ways to put secret things in my test to see if a student is cheating. And unfortunately, they work well. And I have caught students cheating. I will do what's in my syllabus. Please don't cheat. I will catch you, unfortunately, but don't. You've done the problem sets, you'll do okay on test 1. And by now, you should know the alkyl groups. 1 carbon is methyl, attached to a ring or chain. 2 is ethyl. 3 is N-propyl. The other 3 to the end, N-propyl, center carbon, isopropyl. The only 2 butyls, 4 carbons. So the N carbon is N-butyl. To the center carbon with 3 other carbons attached to it, methyl groups attached to it. We call that tert-butyl, or you can write down, which I'll be doing the rest of the semester, because I'm a lazy organic chemist, T-butyl. Now, where can you find alkanes? Oh, I just mentioned this. Natural gas, well, I didn't mention that one. Methane is an alkane. The propane you use for your barbecue is an alkane. Gasoline is an alkane. Vaseline, baby oil, and half the weight of candles is are alkanes. Now, I only taught you one general chemical reaction. Hopefully you've been memorizing this. Hint, hopefully you've been memorizing this. And the first one is combustion. And I could have also had here, which I didn't put here. I can't because this I made on my software. It could also be a cycloalkane. I'll never ask you the formula. I just happen to put it in there. But with oxygen, you need a spark, but I don't have that down there. You get carbon dioxide, water, and heat. You don't have to put the heat down. And remember, as I went through problems and problem set for this chapter, you don't balance equations. So if I have propane oxygen, you'll get CO2 and water. If I have butane and oxygen, you'll get CO2 and water. But you don't balance it. All right, next I talked about the alkenes and alkynes. An alkene is a carbon-carbon double bond. An alkyne is a carbon-carbon triple bond. Double bond showed by 2 lines, triple bond showed by 3 lines. Now, you should know that an alkene, a double bond, is made up of 1 pi bond and 1 sigma bond. An alkyne, 2 pi bonds and 1 sigma bond. The other thing you should know, each one of those lines is a pair of electrons. I'll say that again in slow motion. Each one of those lines is a pair of electrons. So in a pi bond, you have 2 electrons, sigma bond, 2 electrons, the double bond, 4 electrons total. All right, now we went through the Iupath names, and for an alkene, you take the ane ending of the longest chain with both carbons in a double bond, name it as an alkane, drop the ane ending, replace it with ene, and you have a number for acyclic. And if it's sister trans, no number, or sister trans for cycloalkenes. What I don't have here, also for cycloalkenes, and we went through this in the problem set in my lecture, so you can always go back and look at the videos, and that is 1 of the carbons of the double bond, and a cycloalkene is always 1, the other is 2. Now, let me just remind you about cis and trans. Cis is same size side, trans is opposite side. Remember, the bond angle on a double bond is 120 degrees, which is why when I'm showing stereochemistry, which I am, you see how I'm drawing it for the double bond. And the longest chain in A is 4-butane, double bond, butene. The carbon that has the lead carbon closest to the end of the chain is 2, so it's 2-butene. And if I had a plane like that, notice both hydrogens are below the plane, same side. And same side would be cis. So that's cis-2-butane. Same plane for here. And the longest chain is 4 carbons, double bond, butene. 1, 2, it's 2-butane. Notice the hydrogens are on opposite sides of this plane. And opposite, so that would be trans-2-butene. Cis, the hydrogen same size, trans opposite. Now, in real life, in organic, it could be other things besides hydrogen. But for my class, don't tell anybody I'm being nice. I'll keep it to hydrogens. And most of the time in our world, that's true too. And for a triple bond, you can't have cis or trans. You find the longest chain. Oh, there's a mistake here. I'll have to redo this whole thing later today. Repost it. For a triple bond, I'm glad I caught it. You have a triple bond. You find the longest chain with both carbons a triple bond. You change the ane to yne and a number which carbon of the triple bond is closest to the end of the chain. When you're numbering a chain, Don't forget, start only at the ends, not somewhere in the middle with number one. Number one can only be at the ends of the chain, no, not anywhere else. All right, now we talked about general reactions, and general reactions help you determine what are the product or products. And let's go through the first one. Anytime you have a double bond react with hydrogen and catalyst, catalyst can be nickel, platinum, or palladium. You break the pi bond and each carbon gets a hydrogen. Now, normally in a review, I won't do a reaction, but I want to, since it's the first test, remind you the following. All right, everybody, thumbs up, people. Do you see the reaction on your screen now? You see that? Thank you. All right, so when you look at a molecule, you should always look for what's different. What's not a carbon-carbon single bond or a carbon or hydrogen should get your attention like that. And we have a double bond. As soon as I see that, and the rest are just carbon hydrogens and carbon-carbon single bonds, all I see is that I'm reacting with hydrogen and a catalyst. And the catalyst can be nickel, platinum, or palladium. In this case, nickel. And this is something hopefully you've memorized. You break the pi bond. So remember, it's one pi bond, one sigma bond, and each atom of the double bond gets a hydrogen. Now, the reason I'm showing you this reaction is to remind you. First thing, always remember 4 bonds to carbon. The second thing, do you break carbon-carbon single bonds? No, you don't. So I start with 3 carbons. I better end up with 3 carbons. The 2 carbons in double bond, I broke the pi bond. They're only one line, not 2. Each one gets a hydrogen. And now I know there are 4 bonds to carbon, and I can put in the rest of the hydrogens. And the key thing is, do you break carbon-carbon single bonds? No. Pi bonds, yeah, I can break like that. Single bond, except for combustion, which you burn something, and this isn't it. All right, next reaction you should know, if you take a double bond, react it with halogen gas, X2, where X can be fluorine, chlorine, bromine, or iodine, then you break the pi bond, and each carbon of the double bond gets a halogen. Now, these are symmetrical additions. What happens when you're not adding the same thing? And again, do you break carbon-carbon single bond? No. Well, here, let's look at double bond reacting with HX, where X can be chlorine, bromine, or iodine. You break the pi bond, one carbon gets the hydrogen, the other gets the halogen, and it follows Markov-Nikov's rule. The carbon with the most hydrogens gets the hydrogen from HX, and the other carbon gets the halogen. Again, the hydrogen with the carbon with the most hydrogens in a double bond gets the H, the other gets the halogen. And let me just show you what that really means, because it's an important thing, Markov-Nikov's rule. And the question would be, give the organic product or product for the following. And you look for what's different, what's not a carbon-carbon single bond or carbon or hydrogen atom. And here we have a double bond. We're acting with HI. This is a halogen, which we show by X. X can be chlorine, bromine, or in our case, it's iodine. And I apologize, I just did cursive, and some of you don't know how to read cursive, so there, or. Now, what happens? You break the pi bond, one carbon gets H, the other gets the halogen, and it follows Markovnikov's rule. And that is the carbon of the double bond. We're looking at these two carbons, which are these two. You look how many hydrogens. This has one, and this has two. And now we have to use that tough math skills from my class, which is the larger number, and hopefully you pick two. So do you break carbon-carbon single bonds? No, but we did break the pi bond. So I'll have three carbons. This carbon, because it has more hydrogens, will get the hydrogen from HI, HX, and the other carbon right here will get the halogen, X is iodine. And then there's 4 bonds to carbon, the iodine counts as 1 bond. I can put in the hydrogens. And that's how you do it. And that's Markovnikov's rule. Again, the carbon with the most hydrogens gets the hydrogen from HX, the other carbon double bond gets the iodine. Now, if you get those switched, I'm going to give you 0 points because you showed me you didn't know Markovnikov's rule. So it's important where you place things in organic chemistry. Just like if you were having an operation, would you want the doctor to operate on your right hand when it was supposed to be the left hand? No. And also, if you've ever been in operating rooms before where they put a marker on you so they make sure they don't make that mistake. When I had cataract surgery this last November, and anybody needing a great eye surgeon, email me. Each time I was 2 weeks apart. So they gave you time for your eye to heal and everything, even though the next day was pretty much healed. They put above your eye a little X with a washable marker that way they knew they're working on the right eye or the correct eye. But anyways, I just wanted to show you this. And another way of thinking of Markovnikov's rule, the rich get richer and the poor get poorer. We're talking about hydrogens, or them that has it gets it. Why do I still remember that when I learned that? Oh, I hate to say this, but I will. That was back in about 1973, Professor. Whoa, I shouldn't have said that. Long time ago. See how young I've gotten with organic chemistry? All right, let's get back to the review. Next reaction you should know. If you have a double bond and reacted with H+, H+ is an acid catalyst. That can be sulfuric acid or others. Remember, H+ indicates a proton donor, which is what an acid is. And then we have water, H2O. Now, think of water as H and OH. By the way, OH is hydroxyl group. I'll never ask that on a test, but I'll use it in the class. I just did. And here, same thing. You have a double bond. One carbon gets the H. In this case, the other gets the OH. How do you figure which goes which? Markovnikov's rule. Now, we moved on to triple bonds, and I don't have it here. And triple bond has 2 pi bonds and 1 sigma bond. And since organic chemists are lazy, and we are, I don't want to have to balance this equation unless I absolutely have to, which in this case I don't. So to show you need more hydrogen, I use bracket, the letters X and S, and close bracket. That stands for shorthand XS. We're even so lazy we don't even want to spell that. Are we lazy or what? Well, anyways, don't answer that. And that tells you have all the hydrogen in the world with anything hydrogen can react with. With a catalyst, which can be nickel, platinum, or palladium, 2 pi bonds. Each pi bond, when broken, you put a hydrogen on each carbon of the triple bond. 2 pi, you have something popped up on my computer I just got rid of. We get back to chemistry, organic chemistry. Each carbon of the triple bond gets 2 hydrogens. Do you break carbon-carbon single bonds? No, so you don't. And finally, for the alkenes and alkynes, when we have a triple bond, which is also 2 pi bonds, reacting with halogen gas. Remember, X the halogen for this reaction can be fluorine, bromine, chlorine, or iodine. And again, since we have not 1 but 2 pi bonds, organic chemists do not, and I mean do not want to balance things. We don't have to because we're lazy. Again, bracket X, S, close bracket. And for each pi bond, each carbon of the triple bond gets a halogen. 2 pi bonds, each carbon of the triple bond gets 2 halogens. Now, one thing I don't have in here, but we talked about in lecture. Oh, if you've never seen me do this before, that's my shorthand for starting a new topic or something new. I don't know where I picked that up. I've been doing that for a long time. All right, now when you have more than 1 double bond and they're separated by 1 or more carbons, they react like they're alone. So if I were to take this or react it with, say, HCl, but because I have not 1, but 2 double bonds, I don't want to balance this, so I'll just say excess. That just tells me I have all the HCl in the world that can react with anything HCl will react with. Well, what does hydrochloric acid react with? A double bond. Remember, halogen, HX. And I break the pi bond. Remember, this has 1 pi bond and 1 sigma bond. And 1 carbon gets H and 1 gets X, and it follows Markovnikov's rule. And that is the carbon with the most hydrogens gets the hydrogen, the other one gets the halogen. Now, do you break carbon-carbon single bonds? No. So I have 2, 4, 6 across. And if we look at this first double bond, this carbon has 2, this has 1, which is the greater number? Hopefully I'll pick 1. Nope, 2. I tried to fool you there. 2. So the hydrogen will go here. The halogen, X is chlorine, will go here. Now, if we look at this bond, double bond, this carbon has 2, this has 1 hydrogen, which is the greater number. Hopefully pick 2. So the hydrogen, Markovnikov's rule, will go to this carbon, and the other one, just like the general reaction, will get the halogen, in this case chlorine. I know there are 4 bonds to carbon. And I put in the rest of the hydrogens. By the way, if you wanted to write CH3, you can, but I'd leave it like that. That's one less thing you got to do in your brain, which is always good. The less you have to use your brain on a test, the less chance of mistakes. All right. Let's go on to aromatic compounds. The first thing I taught you was this is the structure of benzene. And aromatic compounds, I'll never ask how many pi electrons, but each double bond is a pi electron. They're all holding hands. That gives you stability. Now, when you have a methyl group on a benzene ring, we don't call that methylbenzene. It has both the Iupath in common name, and benzene is the Iupath in common name for that molecule. But for a methyl group, CH3, on a ring, that's called toluene. and these you should know. Now, important thing I need to remind you. If I ask on tests, say, a nomenclature question, 3 points each, draw the structure of benzene. Well, this is one possibility. This would be another, called another resonance form, which I'll never ask about. Or the one I don't like, but it's totally correct, use the delocalized pi. You have to put something inside the ring to show there are pi bonds there. These are the 3 ways to do it. If you were to do this, you get 0 points. Why? Because this is cyclohexane, not benzene. Oh, I forgot to mention another thing I'll do in a second. So don't forget, put the bonds in the benzene ring, and also when you're drawing reactions, don't forget, or use the delocalized. Don't do it this way. Now, the other thing I just forgot to mention, I'll do it again. If I ask, give the Iupath name for this molecule, it's got 5 carbons. Remember, every bend in a line is a carbon. 5 carbons is pentane. But because it's a ring, you need the cyclo. It's cyclopentane. Don't forget that. I've had students, if you just put down pentane, that's wrong, because pentane is acyclic. This is a ring. You need the prefix cyclo. How are we doing time-wise? Doing good. All right, now when you have di substituted, we use the prefixes, not numbers. 1,2 di substituted is ortho, 1,3 is meta, and 1,4 is para. Remember, if you have benzene, the methyl group counts as one of them. Then I introduce some new substituents. Cl is chloro, F is fluoro, Br bromo, I iodine, which is iodo. And then NO2, not NO3, NO2 is a nitro group. And you should know, we went through the aromatic problem set, and you can watch the video on how to do this. Now, for reactions, because I'm not going to teach you about directors in the classroom, we'll do a lab so you get experience with it, but not on a test. I will always start aromatic reactions with benzene. And we already went through the aromatic problem set last week. So, and look at the video if you don't believe me. I don't lie to my students, so it's there. When you have a benzene ring and react with halogen gas and ferric trihalide, you do not break any of the double bonds because you'll lose a lot of stability. It's not going to happen. What happens is you replace one of the hydrogens on the benzene ring with something. And the first case is, say, halogen, either chlorine or bromine. Now, the second one, nitric and sulfuric acid, form the electrophile, something that wants negative charge, the pi electrons, NO2 plus. And that's what attacks the benzene ring and puts on an NO2 group. This is called nitration. Because I'm not doing any substituted benzene ring starting materials, that's the only reaction I can ask you on test number 1 for nitration. Similarly, on test number 1, this reaction right here, SO3 plus H2SO4, sulfuric acid, you put on a sulfonic acid group, SO3H. Now, common mistake on test 1, students forget the H here, and I mark it wrong, because there's no such thing as SO3 on a benzene ring. It's SO3H. Also, it's not SO4H, it's 3. And finally, Friedel-Crafts alkylation. We're doing good on time. When you have a benzene ring reacting with Rx, R is the variable organic chemist used, anything with carbon, hydrogen, X is a halogen, chlorine or bromine. You need aluminum trihalide. You put an alkyl group on the benzene ring. The R is bonded, the carbon with the halogen is the carbon in R bonded to the benzene ring. Oh, it even says that. Bond from ring to R is to the carbon atom in R that had the halogen bonded to it, X halogen. Wow, whoever did this did a good job. Thank you, Dr. White. You're welcome. You always got to thank yourself. Makes life much more fun. And why don't you try this one? What would be the product or products for the following reaction? 3 points each. Oh, after test 1, you'll understand why I call my practice problems. Hint. And when you're done, give me a thumbs up. In case you haven't memorized it yet, hopefully you should have, I'll go back to test 1 review. Here's a quick review of the last reaction. And when you're done, give me a thumbs up. All right, I think everybody's done. So what do we have that's different here? Ooh, a benzene ring. Got double bonds in it. That's different. If we look here, carbon with a halogen, that's alkyl halide. And we have a catalyst, aluminum trihalide. Remember, X can be chlorine or bromine. And this is Friedel-Crafts alkylation. And you do that very special thing. You make a carbon-carbon single bond, very special. What's my R group? This isopropyl. So I'll have my benzene ring. Don't forget to put the bonds in the center or that cyclohexane. I'll mark it wrong. And which carbon had the halogen of the R group? The center one. You break carbon-carbon single bonds? No. So that's that. I know there are 4 bonds to carbon. And I'm done. I just made isopropyl benzene. If I look at the clock, it's time for a break. Let's take a 5-minute break. I'll see you at 1:55, so I can get up and stretch. I've been sitting for a while, and so have you. See you in 5. Time to get going. Welcome back, everybody. Don't forget, Wednesday, I'll be sending out the password for test number 1. And don't forget to have it done and uploaded by, I think, 11 a.m. on Thursday. Gives you plenty of time. Now, one of the things, I'll send out an email. I think I might have picked times for my office hours that don't work for a lot of you. I'm going to send out, and I haven't decided when, but I think I'll change my office hour time slightly. I can do that. And I'll ask for your feedback if that makes anything better for you. I'm thinking of Tuesday, and maybe Wednesday from 6 to 7:15. And I'll send that out. I've got to still think about it. I'll do it today or tomorrow. Won't start this week. Don't forget tonight. And why did I do this tonight? But anyways, tonight at from 5 to 6:15, I'll have my office hour on Zoom. Feel free to come by. All right. I think we covered everything on test number 1 review. One thing I do want to mention, and let me close this first. And let's see. If you notice on your screen, the reaction I just did in class, every time, and I always will do this, I always write the general reaction underneath. On a test, do you have to do that? No. Some of my best students have never done that. And some of my best students always do that. However, in my mind, I always think of those general reactions because those are roadmaps to help me get to my answer, which in this case was that. So that's all you have to put down, but I'd highly recommend if you write it underneath, that will help you get to the right answer. But either way is okay on the test. All right. Are there any questions about anything concerning this Wednesday's test number 1? Going once? Going twice? It's like an auction. Going 3 times? So, well, you didn't buy anything. I said it was Bad Humor Monday. It is. All right, let's move on. We're going to go on to alcohols. This will not be on test number 1, but it will be on test number 2. Now, I finished off last Wednesday talking about phenol. I know you people pronounce it phenol. And this is a molecule where you have a hydroxyl group, OH, on a benzene ring. Remember, we're talking about alcohols. And just to remind you, carbon with a hydroxyl group. Remember, OH is called a hydroxyl group. It's not a functional group, but when it's on a carbon, we call it an alcohol, and that is the functional group. So carbon with an OH group, hydroxyl group, is an alcohol. And I don't know if I mentioned to you, one of the products I've been using for many years, I don't get any kickback money. I got to find a way to get product placement kickback. Like every time I do this, they send me a check for, I don't know, $250. Nah. Anyways, this is great stuff, Carmex. And if you look on the label, it says phenol. You can't see it, but it's there. And the phenol in here, when you put it on your lips and you get that tingly feeling, that's what caused it. It's got antimicrobial, antibacterial properties, which help heal things if you have any problems. It also helps your lips, the other components and their chemicals, to make your lips from going dry, especially in the winter. All right, next couple of slides, watch closely, click. Will these be on a test? No, but they give you background information, and you might need this for other classes you take. Now, alcohols can hydrogen bond. What is a hydrogen bond? It's the weak intermolecular. Now, the term prefix inter means between two things. Like if I'm going on an international flight out from O'Hare Airport, which I have many, many times, like if I were going to, unfortunately, with the funeral, I wouldn't, but to London, which I've been, Manchester, or if I'm going to Amsterdam, all those cities I've been to many times, national flight means between two separate countries. Now, intermolecular means between two different molecules. So a hydrogen bond is a weak intermolecular attraction between non-bonding electrons on nitrogen, oxygen, or fluorine, and the hydrogen atom that's bonded to those. It's a weak reaction. It's not a real chemical bond, but it's weak. It's weaker than like I have here, a single bond, but it has significant physical effects on physical properties, such as boiling point and solubility. And alcohols can hydrogen bond to each other and water. And what do I mean by hydrogen bond? If you have water, there's a slight polarization. This is the Greek letter delta, but it's small case. Delta, you're probably familiar with this. We don't usually call it upper or lowercase, but it's uppercase delta. And in chemistry and science, this means difference. If I can spell it. And the smaller one means little difference or slight difference. So there's a slight positive charge on the hydrogen and a negative on the oxygen, same over here. And if we have another water molecule, same thing happens, slight positive charge, slight negative, slight positive. And this is a negative, this is a positive. Opposites attract, and there's a slight, it's called Coulombic or electrical attraction, and this is the hydrogen bond. Now you might say, so what? Well, here's water. And water, if you notice at room temperature in my house, I don't know, I think right now up here where I am, it's about 70, give or take a degree or two in my office. It's a liquid. If it wasn't for hydrogen bonding, that weak little attractive force between the hydrogen and oxygen, this would be a gas right now, and it's not. And that plays an important role in life on our planet. Think about it. If all our oceans were gases and not liquid, life would be different. Your blood, which has mainly water, oh, I wonder what I scratched myself. Anyways, your blood has mainly water, and it's a liquid. If it wasn't for hydrogen bonding, it couldn't be a liquid. We'd look a lot different. I wonder what that would be. But anyways, alcohols can do the same. And hydrogen bonding, again, switches off, but I just wanted to, for other classes. And alcohols can hydrogen bond to water and also other alcohols. And that gives it higher boiling points and melting points and solubility. Now, I should tell you this, bartenders don't like being told, you know, you can put alcohol in that drink because alcohols can hydrogen bond to water. Bartenders don't like being taught organic chemistry. So don't, trust me, don't. Now, let's talk about the acidity. Again, switches off about alcohols, phenols. Alcohols are weak acids, but their conjugate bases are strong bases. But phenol is different. It's a much stronger acid. That's why you feel that tingly feeling, part of it on your lips, because it's an acid. And this is due to resin stabilization. See board, I better get to work. Again, switches off, but you may need to know this for other classes in the future, which is why I'm going it. Now, an acid is something that gives up a proton, and the bigger arrow means it's not going to go to the right. It's a very, very weak acid. But that makes this alkoxide a very strong base. Now, Dr. White's going to have some Dr. White fun. Phenol gives up its proton to give this. This is called the phenoxide anion. But I can draw different resonance forms. And all I'm doing is moving electrons around. This is not going to be on its S, but my last patent dealt with phenoxide anion, what other people didn't know what you could do with it. So I'm having some fun. I can draw another resonance form. Now, you know, I'm an organic chemist, so I'm having fun, and I am. And the more resonance forms you have, the more stable it is. So that makes this more stable than this alkoxide when ours is carbons, no benzene ring. And therefore, it's easier to go to this, and that's why this is a stronger acid. Again, this won't be on its S. Now, alcohols can be weak bases. They can be protonated. In other words, i.e., I've used this once in a while. Are you all familiar with the term abbreviation, i.e.? That's Latin, and I don't know the Latin words, but in English, that means that is. That's a shorthand of writing that is. They react with strong acids. And this is the first reaction in two important reactions of alcohols, first step. What I mean by that, and again, switches off, I take an alcohol and react it with strong acid, H+, the non-bonding electrons attract that and form this intermediate. I put it in brackets because it's not really isolated. Now, do you see something right here? Hydrogen, hydrogen, oxygen. What's got two hydrogens and oxygen? What's got H2 and O? Water. And whenever you can form a stable leaving group, it says, I'm out of here. and you get this. This is called the old name, which I like better than the new name. This is called the carbonium ion. Now they call it the carbocation. I don't like that new name, so I use the old one. I'm old-fashioned on this. And that's a very reactive species, which in a number of steps you'll see is a key step where you react an alcohol with acid and then something else. So this means what's a base? Something that accepts a proton. So in this reaction, this step, this is a base. So alcohols can be either weak acids or weak bases. It's called amphoteric. And again, switches off. This won't be on its test. All right, click, switches on. Now, one thing I haven't told you about my test, I only put on my test, not the final, but my test material that I covered in that area just for that test. Now, the following reaction, I believe, is the only reaction that will be on test 1 and can be on test 2. Why? It's the synthesis of an alcohol. And what synthesis means how to make an alcohol. If you take a double bond, react with acid and water, you break the pi bond, one carbon gets H, the other gets OH, and it follows Markovnikov's rule. So once again, and this can be fair game on both test 1 and test 2. I think that's the only reaction I do that with. So here's general reaction. We just covered it in a review. You've done this. So instead of me doing one, I'm going to let you try one. And here we go. Give the organic product or products for the following reaction. 3 points each. And don't forget, today's lecture will be on YouTube later tonight. I hope that's all helping you being able to watch this again if you need to, or watch it for the first time if you can't make it to my lectures on Zoom. And when you're done, don't forget, give me a thumbs up. All right, time for me to get to work. How do you do this? You look for what's different, what's not a carbon, carbon single bond, carbon or hydrogen should get your attention. Ooh, a double bond. Reacting with H plus, which is acid catalyst, water. Remember, water is H, OH. This has one pi bond, one sigma bond. I break the pi bond, not the single or sigma bond. One carbon gets H, the other gets the hydroxyl group OH, and it follows Markovnikov's rule. The carbon with the most hydrogen gets the hydrogen, the other gets the hydroxyl. Well, now we got to use our high level mass scale. How many carbons, how many hydrogens are in each carbon of the double bond? 2, 0, which is the greater number? Hopefully you pick 2. Now, do you break carbon-carbon single bonds? No. So I started with 3 carbons in a methyl group there, better end up. But I did break the pi bond. Here are my 2 carbons, the double bond, no longer. And the first carbon gets the hydrogen, and the other gets the hydroxyl group. And there are 4 bonds to carbon. And I'm done. Oh, let's do another one. These are fun. And here's one more for you to have fun with. Am I nice or am I nice? Don't answer that. Oh, excuse me. A yawn just slipped out. Thank you, Ignacio. Thank you, Andrew. All right. What do? We look for what's the, ooh, a double bond in that ring. What am I reacting with? Acid and water. And remember, water is HOH. Break the pi bond. This double bond has 1 pi bond, 1 sigma bond. And pi bonds I break, sigma, single bonds I don't. 1 carbon gets H, the other gets the OH, and it follows Markovnikov's rule. And that is the carbon double bond with the most hydrogens gets the hydrogen, the other carbon gets the hydrogen. Oh no, I don't see any hydrogens on a ring. You've got to count them. Use 4 bonds to carbon. Let's look at our 2 carbons. This carbon up here has 3 bonds to it. 4 minus 3 would be 1. So there's 1 hydrogen up here. This carbon has 1, 2, 3, 4. 4 minus 4 equals 0. So that has 0 hydrogens. Which is the greater number? Hope you all pick 1. And it is. Do you break carbon-carbon single bonds? No. So I'm still going to have my ring, and I'm going to still have my methyl group, CH3. I don't show the hydrogen there, but the hydroxyl group will go to this carbon, which you can draw it this way, or you could draw it this way. And that's how you do it. Oh, let's do a synthesis problem. Unlike test 1, which only have one synthesis. Test 2 will have 3 or 4. Any more would be cruel, unusual punishment. What would you react with water and acid to make that compound? Well, I'm really working your brains today. That's a good thing. Thank you, Andrew. And we'll wait for everybody to get done. All right, everybody's done. Thank you, Ignacio. All right, so how do we do this? Well, you look at the product and what's different. What's not carbon, what's not hydrogen. Ooh, oxygen with a hydrogen on a carbon. That's an OH group or an alcohol. And what do I react with acid and water to put in a hydroxyl group? A double bond. And the adjacent carbon, one next door, gets the hydrogen. Now, let's look at this reaction, how you work backwards. The carbon with the hydroxyl group has to be one of the carbons of the double bond. The carbon with the hydroxyl group has to be one of the carbons of the double bond. And then a carbon next to it has to have a hydrogen. Well, here's our carbon with the hydroxyl group. This carbon next to it has no hydrogens, but this one does. So the double bond has to be between those two carbons. Now, do you break carbon-carbon single bonds? No. So I end up with 6 carbons. I better start out with 6 carbons, and they're placed the same way. Now, this carbon with the hydroxyl group has to be one of the carbons of the double bond. And the only other carbon in this molecule adjacent to it, next to it with hydrogens, is that. So this is the other one that has to be the double bond. And now there are 4 bonds to carbon. Remember, 4 bonds to carbon. And that's the molecule. Now, I drew this a certain way to illustrate a point. Why didn't I put the double bond to this carbon? Well, let's look what will happen when you do that. I'm going to do it in red because it's wrong. All right, this is the wrong structure. See, it says wrong. We look at this carbon. How many bonds to carbon do you see on that drawing? Count them. 1, 2, 3, 4, 5. Can you have 5 bonds to carbon? No. So remember, when you draw a structure, your friend, 4 bonds to carbon, every structure check where you made a change, there can only be 4 bonds to carbon, not 3, not 5, because this is wrong. That's why I give it 0 points. All right, let's move on. Now, in coming weeks, when I go through new functional groups, we've done the nomenclature. We've talked about some, not really, I haven't, said a little, some applications, real world uses. And then how to make them. We just saw how to make alcohol. There are other ways, but we'll learn later chapters. And now let's talk about reactions of alcohols. Once you have it, what can you do with it? Now, before we do this reaction, I'm going to stop share. Everybody take a deep breath. Let it out. Take a deep breath. Let it out. Are you all nice and relaxed now? Then take another deep breath. Let it out. Now are you all nice and relaxed? All right, stay that way. The next reaction I'm going to show you, relax, is one of the more difficult reactions for students this semester. At first, you're going to look at it and say, ah, I don't know if you're going to go, ah, but you're going to not, what's going on here? Sort of confused. I'm going to only show one example today. Then I'm going to let you try it in a problem set. We do the problem set, I'll come back and do some more. But this is a tough reaction. So if you're having problems, guess what? So did I when I first learned this. Took me a while to wrap this around it. And that's dehydration of alcohols to double bonds. What's dehydration? That means loss of water. If you have an alcohol and a carbon with an adjacent hydrogen reacted with sulfuric acid, this little triangle means heat in organic chemistry when it's used in a reaction like this. And sometimes I'll even put the temperature, high heat, 180 degrees is pretty high. And you'll lose a hydrogen and a hydroxyl group to form the double bond. Now, do not write this down. When you have 2 possible choices of double bond, this was an important problem to solve. Another great Russian organic chemist, Zaitsev, came up with a rule. Do not write this down, but his rule states the major product in the intramolecular, that means in the same molecule, as opposed to different molecules, alcohol dehydration, loss of water, is the alkene that has the greater number of alkyl groups attached to the carbon atoms, the double bond. And you go, huh? Well, let's take a look at this. And let's look at this reaction. First of all, the general reaction. If you have an alcohol carbon with a hydroxyl group and an adjacent carbon, one next door with a hydrogen, and you react it with sulfuric acid and heat, this means heat, you'll lose water. Remember, I don't show plus water because organic chemists are biased against inorganic. If I don't have to worry about it, I'm not going to put it down. but you'll form a double bond and it follows Zaitsev's rule. So let's take a look at this. All right, now everybody see that reaction on your screen right now? Thank you. All right, now what's different? Ooh, what's not carbon? What's not hydrogen? Oxygen with a hydroxy group on a carbon, that's an alcohol. And if I have an adjacent carbon, one bonded to this carbon with a hydrogen, and I react it with H2SO4, which is sulfuric acid and heat, I'll lose the water between these two carbons. I'll form a double bond, and it follows Zaitsev's rule. Well, let me teach you Zaitsev's rule. Here's the carbon with the hydroxyl group. I have an adjacent carbon on A or B. Now, if I were, let's do A, B. I'm drawing it up here because I need more room. Now, if I lose the hydrogen from A and the hydroxyl group between these two carbons, I'll form a double bond. Do you break carbon-carbon single bonds? No. So I'll still have my 4 carbons, but now I've formed my double bond. And let me put in my hydrogens because I like to do that. Remember, there are 4 bonds to carbon. Now, if I lose the hydroxyl group and a hydrogen from B between this carbon and the hydroxyl group carbon, I'll form a double bond. Do you break carbon-carbon single bonds? No. So, but now the double bond will be there. So everybody see how I got to this point? And put in the hydrogens. Again, the general reaction is hydroxyl group carbon, adjacent carbon with a hydrogen, sulfuric acid and heat. I'll form a double bond between these two carbons. Well, here in the top, here's my hydroxyl group, but I have a hydrogen on A, hydrogen on B. If I lose the hydrogen atom and the hydroxyl group on hydrogen from A, I'll form compound A. This is between the two carbons. I'll form my double bond, and I did. Now, if I lose the hydrogen from B and the hydroxyl group, I'll be forming a double bond between these two carbons and everything else that comes along for the ride. Now, pay attention. Here's how you use Zaitsev's rule. You count the number of carbon atoms directly bonded to the carbons of the double bond. You count the number of carbon atoms directly bonded to the carbon of the double bond. In this case, it's only that one. You don't count these because those aren't directly bonded to the carbon of the double bond. If we look at B, how many carbon atoms are directly bonded to the carbons of the double bond? Well, look at the blue circles, and the answer is 3. Now, in real life, B, which is the more carbon atoms directly bonded, would be the major product. You get mostly that, and A, you just get a little bit. For my class, to make your life easier, I will do Zaitsev's rule and say that's your answer. okay? You get the answer the way I'm going to teach it, which in all realistic, being truthful, is really the way I think of Zaitsev's rule. In real life, that's the main thing you get. So you count the number, and this is important, carbon atoms directly bonded to the carbons of the double bond. Not all of them, just the atoms directly. In carbon A, answer A, there's only one. In answer B, there's 3. And the answer is the one with the higher number. And that's how you do Zaitsev's rule. See, I wasn't lying to you. It isn't that simple at first. And if your brain's going, what the heck is happening? Come back and watch this again. You can do that on the video, and I'll go through this again. Now is not time to do another one. I've done this enough times to know, do it once, let students have time to analyze this or digest it in their brain, and then we'll come back and you'll see it's not that hard. Okay? Let's move on. Now, well, all right, I'm sorry about this. Let's try an experiment. Nope, that didn't work. Hang in there while I have to do my close Microsoft Word. I think I opened up too many files or something. I've got memory ordered for this machine, just hasn't come in yet. Hold on, let me do this. Let me close this. Let me open them up again. Sorry about that. I think with my tablet, my webcam, and all the things I have going on, I overload it over after a while. It only happens when I teach a double class, one in the morning, one in the afternoon, which I have, and I have to do that. All right, back to our regular station. And next reaction, let's talk about, and this is a lot simpler. If you take any alcohol reacted with HX, you replace the hydroxyl group on the carbon with the hydroxyl group with the halogen. Again, if you take any alcohol reacted with HX, and you'll get water too, but you don't have to write that down, it's inorganic. Yeah. But anyways, let's take a look at this reaction. General reaction, any alcohol plus HX, you get an alkyl halide. That's what this is called. And X here is chlorine, bromine, or iodine. I mentioned a long time ago when we were using HFX with double bonds, when X is fluorine, HF, that's probably one of the most dangerous chemicals I know, and you never mess with that. That's not the way to put a fluorine on a carbon. There are safer ways. So let's take a look at this. And sometimes I'll write it over the arrow, but that's the same thing. And if we look at this molecule, the question is, hold on, that's the most ugliest looking hydrogen on an oxygen. That's better. What's the product or products for the following reaction? Organic products. Well, you look for what's different. Ooh, oxygen with a hydrogen and a carbon, that's an alcohol. Ooh, I'm reacting with HCl. Well, I know halogens are X. X can be chlorine, bromine, or iodine. I replaced the hydroxyl group with the halogen to make an alkyl halide. And later in the semester, you'll see why this is a useful molecule, because we can use those type of molecules, RX, with other reactions. Now, do you break carbon-carbon single bonds? No. So I have 1, 2, 3, 4, 5 across. I better end up with 5 across. The carbon with the hydroxyl group will be the carbon with the halogen. What's X? Chlorine. And that's the answer you should get. So when you do this reaction, you look for what's different. Carbon with a hydroxyl group, alcohol, reacting with HX. What happens? You replace the hydroxyl group with the halogen on the carbon the hydroxyl group was. You put it elsewhere, I'll mark it wrong, because it is. And putting it elsewhere will give you another isomer that may or may not help you make what you're trying to do. You know something? I'm looking at the clock. I'm going to give you an extra 30 seconds during the break. Don't tell anybody I'm being nice. Now would be a good time to stop, take another break, come back at 2:50, and we'll continue. Let's take about 5.5 minute, 1.5 minute break. Well, if I keep on talking, it won't be. I'll see you at 2:55. I'm back. Hopefully you are too. All right, home stretch. We're talking about this reaction. If you take an alcohol, react with an acid, HX is an acid like hydrochloric, hydrobromic, or hydroiodic acid, you'll replace the hydroxyl group with the halogen on the carbon that had the hydroxyl group. So I better let you have some fun. And here's one for you to have fun with. Thank you, Ignacio. Your friends call you IG?
Junior. I'm a junior, so
You're what?
I'm a junior, so junior.
Really?
Yeah.
In my family and I think in our religion, we don't do that. We never name anybody after someone else. So I can't think of all the people I know, and we're talking about Jewish religion. I've never met anybody who's junior.
Hmm.
We just don't do it. Not that there's right or wrong.
I didn't know that. Wow.
So I don't know if that's a tradition or a reason behind it. I just, of all the people I know, family and outside, I've never met anybody named after their father or grandfather like that. So people call you Junior, and I bet you hate it.
Well, I'm
look
fine.
With it?
I've been called worse things.
Guess what? So have I. All right,
Yeah.
continue on. Thank you for sharing. All right. What's the product or organic product or products of the following? Look for what's different. Carbon, oxygen, hydrogen, a carbon, alcohol. In case you forgot. And we're reacting with a halogen, we call that HX. Remember, X for this reaction could be chlorine, bromine, or iodine. And what happens? The carbon with the hydroxyl group is replaced with the halogen. Now, do you break carbon-carbon single bonds? No. So I got 3 across plus a methyl. Which carbon has the hydroxyl group? That will now have the halogen. You can write it down or across, doesn't matter. And I know there are 4 bonds to carbon, and the halogen counts as 1. And I'm done. Ooh, that rhymes. And again, replace the hydroxyl group on the carbon with the halogen from HX. In this case, it's iodine. Oh, this is fun. Let's do a synthesis problem. what would I react with HBr, hydrogen bromide, or hydrobromic acid, to form that molecule? Dr. White loves rings. I'm happy. And don't forget, tonight I have my office hour, and Wednesday night too. Thank you, Ignacio. I won't call you by what you don't like called, because I don't like it either. When people call me, I will never even say it. I've hated it since I've been about long enough I can remember being me, meaning about 3 or 4. Thank you, Andrew. My name with a Y at the end, shortened. I won't even say it. It disgusts me so much. All right, let's get to work. How do we do this? How do we figure out, and this is the fun part, the best part of organic chemistry, what would react with HBr to make this compound? Well, what's different? What's not carbon? What's not? Ooh, a halogen on a carbon. And X for this reaction would be chlorine, bromine, or iodine. And what reaction is that? HX. And what do you start with? An alcohol. So do you break carbon-carbon single bonds or make them? No. So if I end up with a ring with 5 membered and a methyl here, 2 methyls, I better start with that. So I did. Now, this tells me the carbon with the halogen is the carbon with the hydroxyl group you start with. The carbon with the halogen is the carbon in the starting material with the hydroxyl group. That's this carbon, which is this carbon, which means I'll do that. And lo and behold, let me clean this up a little. Oops, too much. Let's do this over again. I didn't like the way the ring looked. Instant replay. So the carbon with the hydroxyl group, you'll replace it with a halogen, which is what you do. And that's the fun part of organic chemistry for me. And that's what I've been trained to do. And I worked in industry doing. How do you make something? Now, in real life, they're not going to tell you what do you react with. And in real life, the marketing and sales people will come to you in my position as a senior research and development manager and say, we need this kind of product, or even harder, we need a product that we can make an existing plant equipment that will do this and this and this. And you have to come up with make things that will. And that's the fun part, real fun. And it's not easy either, which is why I had a 6-figure salary when I worked in the chemical industry. All right. Now, what I'm going to write down, you do not have to write down on your notes. What if I had this compound and I wanted to replace the hydroxyl group with a halogen, say chlorine? Well, you say, oh, it's an alcohol. I'll take an alcohol, react it with HX, where X can be chlorine, bromine, or iodine. And I'll replace the hydroxyl group with the halogen, and I'll make that. But look, this also has a double bond. So if I react this with H, say Cl, so I want to convert this to chlorine, this will react, but a double bond you learned for test 1 you can break the pi bond, one carbon gets H, the other gets X. So what can happen? Well, you're going to get a mess, which is not something you want to when you're doing a reaction. Some of this will react like this. Some of it will react like this. And some of it will react like this. Like I said, you get a mess. And this should not be a 2 there. So if I really wanted this, I can have all this stuff present, which is not good. I have a mess. And when you're making something, you want a pure compound. So what do? Well, it turns out this is a problem encountered numerous times in organic chemistry. What you do is you come up with a new reaction. And that new reaction is the reaction of alcohols with thionyl chloride. I'll never ask what thionyl chloride is, SOCl2. And what happens is you replace the hydroxyl group with the chlorine. You also get sulfur dioxide and HCl, which you can put some base in there to neutralize that. But you'll get the alkyl chloride. And I've worked with this stuff. It's nasty because it will want to react with water to give off sulfur dioxide and HCl, which is not good. But you learn how to work with this under what's called an inert atmosphere, where there's no moisture in the atmosphere you're running it in, the vessel you're running it in. So I like to say this is one of those reactions that separates those who are going to become organic chemists from those who aren't, because the first time you run it, it's scary. But after that, you get used to it, and it's like anything else. The more you do it, the more comfortable you are, but you're always careful with it. So let's look at this reaction. If you have an alcohol reacted with thionyl chloride, SOCl2, you'll replace the hydroxyl group with the chlorine on the carbon with the hydroxyl group. Thionyl chloride will not react with carbon-carbon double bonds. So this would be the good thing to do the reaction I had before, which I'll never put on a test, but I wanted to illustrate why come up with new reactions, because sometimes the original reactions have problems. So let's take a look at this. So question would be, give the organic product or products for the following reaction, 3 points. And you look at the starting material, what's different? What's not carbon? What's not oxygen with a hydroxyl group on a carbon? That's an alcohol. Reacting with thionyl chloride. And the general reaction, I replace the hydroxyl group, OH, with the chlorine on the carbon that the hydrox group was on. Do you break carbon-carbon single bonds? No. Hopefully nobody's getting nightmares hearing me say, do you break carbon-carbon single bonds? No. Ooh, that sounds evil. But anyways, it's that important to remember. So I have 3 carbons. Which carbon had the hydroxyl group? This one. I'll replace that with a chlorine. And I'm done. And you'll find out later this semester, put a chlorine on a molecule like that. This allows you to use that as a building block for other things. Just like carpenters, you can use nails or screws or 2x4s. They're useful to build other things, but you first have to know how to make those. And this is the same thing. So it's your turn to have fun. And here's some fun for you to have. I don't know if you had a chance to watch some of Queen Elizabeth's funeral early this morning. One thing for the British, they do know how to put on pomp and ceremony. Their uniforms are magnificent, and the training to do what they did is quite extensive and magnificent. One thing you don't know that I've read about, the ceremonial guards you see in the fancy uniforms, those are picked from the crack, the best troops. You've got to be the best of the best to be one of those gentlemen or women now too. It's a great honor, and you have to be a great soldier to get that great honor. No, so much for world events. Back to organic chemistry. Get to work. I was just thinking in my lifetime, I wasn't old enough to remember when she became queen. So she's always been, in my mind, the Queen of England, the monarch. All right, give me a thumbs up when you're done. Thank you, Ignacio. And I'll be patient and wait for everybody to finish. Don't forget when you're done, give me a thumbs up. All right, let's get going. If we look at this molecule, what's different? What's not carbon? What's not? Ooh, an oxygen with a hydrogen and a carbon. It's an alcohol. And what are we reacting with? SOCO2, thionyl chloride. And you replace the hydroxyl group on the carbon it was with a chlorine. You break carbon-carbon single bonds? No. So I have 1, 2, 3, 4 across, plus a methyl, 1, 2, 3, 4 across, plus a methyl. The hydroxyl group will be replaced with a chlorine. And I know there's 4 bonds to carbon. And the chlorine counts as 1. I can put in my hydrogens. That's how you do it. You replace the hydroxyl group on that carbon when you react with SOCl2, thionyl chloride, with the chlorine. Now, as I mentioned, there'll be a couple, not just one, synthesis problems. So this would be a good reaction to practice it. But hold on, time out, bad Dr. White. All right, this reaction with Zaitsev's rule, dehydration, I will never put a synthesis problem for that on a test or the final. That's cruel, unusual punishment. At least as of now, the Supreme Court has outlawed it, so I won't do it. That's not nice. I won't do things like that. So this reaction, and throughout the semester, there are a number of reactions I'll say you should be able to predict the product or products, but I'll never ask you to predict the starting material. I can, but then again, I have a PhD in this stuff. You don't. You're all starting. So this will never be a synthesis problem, but this one can be. And if I do a synthesis, this could be also. So let's do one. All right, there's one. What would you react with thionyl chloride to make that molecule? Dr. White's happy because it's got a ring, and I love rings. So does Mother Nature. Students don't. Secretly bending your mind how to do organic chemistry. Thank you, Andrew. Thank you, Ignacio. I better get to work. So the question is, what do you react with thionyl chloride to make this compound? Well, what's different? What's not carbon? What's not hydrogen? Ooh, halogen on a carbon? RX. Or better yet, for this one, and why am I doing that? Because of this. I didn't look at first. And thionyl chloride, what do you react with thionyl chloride to make an alkyl chloride? And the answer is an alcohol. And now, remember, the carbon with the hydroxyl group in this reaction is replaced with a chlorine. Do you make or break carbon-carbon single bonds? No. So if I end up with a 6-membered ring with 2 methyl groups, I better start with a 6-membered ring with 2 methyl groups where they were. And I did. Now the carbon with the hydroxyl group will be the carbon with the chlorine, this carbon, which means this carbon will now have the alcohol, the hydroxyl group. And that's how you do it. Everybody with me on that? Any questions? Well, I've got a question for you. And that is, I haven't done it, but we're going to be doing it more and more. And that question is, why am I learning this stuff? Well, the obvious answer is someone said you had to take organic chemistry to get into a program or school, and you want to get a good grade to get into that program or school. But why learn this stuff? Good question. Let's find out. Now, how many of you have heard of artificial sweeteners? I think most of us have. All right, everybody see on your screen Splenda? You see it? All right, now Splenda is one of the two, probably I think the largest, maybe not, brands in the world of artificial sweetener. They're called artificial sweetener because when you get it on your tongue, tells your brain this is sweet, and we've been trained sweet is a good thing. I don't know, has anybody, I've never met anybody, but have you ever met anybody who doesn't like things that taste sweet? That'd be sad. But anyways, what's the main product in Splenda? And that's a molecule called sucralose, which has this structure. Now, every bend in a line is a carbon. Forget about this fancy way of drawing rings, but notice over here, you see the structure on the screen right now of Splenda? It has, thank you, Ignacio, has a chlorine here, a chlorine here. By the way, this bend is a carbon, another bend here, and a chlorine on that carbon. Plus it has some OH groups. Now, there's another molecule I want to open up. And that's this one, sucrose. Do you see the molecule present with all the hydroxyl groups on your screen now? No chlorine. Can you see that? Now, this is sucrose. You also know it as table sugar. Yeah, it's stuff you put in your coffee, tea, or on your cereal or oatmeal or anything else you want sweet. Now, let's go back and forth between the two. Here's sucrose, here's sucralose. And the only difference is in 3 spots in sucrose, I replace it with chlorines. Now, how do you do that? Well, one of the 2 reactions I just showed you. Either react sucrose, table sugar, with chlorine, HCl, or with thionyl chloride. Now, which one does the company use? They don't tell, it's a trade secret, but I would guess one of those 2. So the reactions you've just learned, they help you make this product, which is used in a multi-billion-dollar sales product throughout the United States and the world. Now, how this makes your tongue think it's sweet, but at the same time, 0 calories. Well, the chlorines on there inhibit your body from breaking it down to what's called glucose and absorbing it. How? I'm not going to get into that in this class. Now, the one thing I will tell you is, this is my personal opinion, and a lot of people disagree. Small molecules, and I call this borderline small, with halogens have been known to be carcinogenic, form cancer. Now, there have been claims, sucralose says, Splenda, no, that doesn't happen with our compound. There's no proof to that. And maybe they're right, but Dr. White's not going to take a chance on this. Now, I used to use equal. And time for a personal story. Do I have time? I do. Now, a number of years ago, I'm a cook, and I made some kimchi, and my own kimchi, and I did something wrong, and it was in my refrigerator long enough to give me food poisoning. And boy, it was not fun. and I had to go to my doctor, and he gave me stuff. And I said afterward, I came back when he talked about it. Or when he gave me stuff, I said, well, I read something in the New York Times. Should I do this? And he says, I've read that too, and it is true for me, but I think it would be a good idea. And what was that? Well, a number of years ago, time out for a water break, there's these two stomach doctors, I always pronounce that word wrong, who were overweight and were wondering about how effective is artificial sweeteners in helping you lose weight. So being a stomach doctors, the thing in your stomach is you have probiotics, those little bugs that help eat up your, now I mean, you can see, I don't know biology that well, but that help you digest food and keep you healthy. Well, they did some experiments with themselves and friends who, after they ate food with artificial sweetener, they did both Splenda and Equal, the two most popular artificial sweeteners out. They measured a person's poop and for the probiotics. And they found out both of them killed off most of the probiotics in your stomach and gut, which is not a good thing if you're trying to lose weight. And they were shocked at that. And they decided they would stop using that and going back to sugar, but in moderation. And they started losing weight. Well, I, up to that point, before I had food poisoning, had been a heavy user of Equal. My sister uses Splenda, I used Equal. And I'd use a lot in my tea. I'd have 3 or 4 mugs of tea a day. And then I'd also, if I had pop, that was Equal artificial sweetener too, like Dr. Pepper or Verner's. Well, the doctor said, you know, it upsets my stomach too. I don't know if it's valid or not, but I think it is personally for me. So I stopped using Equal. Guess what? I started losing weight because I wasn't getting as hungry because of what the Equal was doing to me by killing my probiotics, the flora in my gut. Now, I still have to lose more weight, trust me, I do, but I've been able, I'm eating sugar, but in moderation, not that much moderation. I still have a couple mugs of tea. I put more than 2 teaspoons in a mug, but that's about, and I try and limit sugar and other things I buy, but not by using artificial sweetener. It's interesting, when that happened, and after I saw it had effect, and also I got well, I think that helped me get well better. I also took, you can buy probiotics capsules to help build back what I destroyed when I had food poisoning. In fact, my doctor gave me some free samples, so you should buy this. I forgot what brand I get from Costco every once in a while. But anyways, I had a bunch of pop in my house and Equal, and I teach at College of DuPage, and I know the people in the dentistry clinic. And I said to the director, if I bring in a couple of cases of pop that are diet, you think your people will drink it, like it? And she said, sure, bring it in. I did, got it out of my, instead of throwing in the garbage, it went to good use. But that's my personal opinion, but that is true about what the doctors found. So when the things you're learning, the general reactions you're learning are used as building blocks to make molecules, the ones examples I use in my class, now you're probably not going to find now later on, or we'll do some in your daily life. However, they are used to make things that you do find in your daily life, like artificial sweetener. All right, let's move on. Now, before I move to the next reactions, there's something I need to teach you that's not in a slide, so I'll do it on my whiteboard. Now, when it comes to alcohols, there are 3 different types of alcohols. What I'm going to teach you, I'll never put on a test or a final, but I'll use this terminology in class. All right, now right here, when you have one R group on a carbon with a hydroxyl group, that's called a primary alcohol. Again, I'll never ask this on a test or the final, but I'll use this terminology throughout the semester. And it's abbreviated like you would the degree sign 1, ROH, ROH being alcohol. Now, if you look at this one, let me hold on one second. Give myself some more room here. Now, notice I'm introducing something new. This is called R prime. And in math, you know you have X and Y, and they're different variables, like X plus Y equals 100. Each one's a number, and it could be different things. Well, in organic chemistry, R is a variable, anything with carbon, hydrogen. R prime, same thing. This just tells you these could be the same or they could be different. R could have 1 carbon, R prime could have 5, R could have 10, R prime could have 2. This, like X and Y, can be different numbers. Now, when you have 2 R groups that can be the same or different on a carbon with the hydroxyl group, we call that a secondary alcohol. And we abbreviate it by the number 2 degree sign ROH alcohol. 1 R group, primary, 2 R groups, secondary, and they can be different. And why did this burp on me? Once in a while. Say Friday the 13th. Actually, I have good luck on Friday the 13th. Oh, it's Monday the 19th. That's why things are going blooey on me once in a while. All right, let's do the last one. And when you have 3 R groups on the carbon with the hydroxyl group, that's called a tertiary alcohol. And in certain reactions, not all alcohols react the same. And that's abbreviated like this. So 1 R group, primary alcohol on the carbon with the hydroxyl group. 2 R groups, which can be the same. That's why we have R and R prime, secondary alcohol. 3 R groups on the carbon with the hydroxyl groups. Notice I have R prime and R double prime. And I'll do in this class R triple prime. After that, you start using letters or numbers like R sub 1, R sub 2. In some of my patents, I've gone up to R sub 15 on different molecules, or 10, I think it was. So primary, secondary, tertiary alcohol. And why did I have to teach you this? Because of the next reaction. This is called oxidation of alcohols. And if you take a primary alcohol, 1 R group, and oxidize it, you'll get an aldehyde. And let me rewrite this. Now, this is a primary alcohol. I'll never ask that in class, but I'll use the terminology. Now, this is abbreviation for oxidation reagent. And this class, I'm not going to make you memorize them. You can have sodium chromate, potassium chromate, potassium permanganate. Those all will do these reactions. But for me, for this class, since you're not going to become organic chemists, if you see a bracket, oxygen, closed bracket. Why? Because the first oxidizing agent organic founds was oxygen gas, which is why we use an O there for any oxidizing agent. What happens is you lose a hydrogen from this carbon, hydrogen from the oxygen of the alcohol, and you form a carbon oxygen double bond. And we'll learn later when we do this chapter, this is called an aldehyde. And Dr. White loves aldehydes. They've been good to me. I've been good to them. Now you can write it and I'll teach you later in the, like this or like this. But I like to write it this way because I think it looks cool. And Dr. White tries to be a cool dude. And this is an oxidation reaction. And I use this reaction in my PhD synthesis research a lot. It's a very useful reaction. So the question is, give the organic product or products for the following reaction. And you look for what's different, what's not carbon, what's not oxygen, hydroxy group and a carbon, alcohol. But when I see the oxidizing reagent symbol, I know you should consider what type of alcohol. And that's a primary alcohol. Remember, general reaction, you don't have to write when you're doing this material for test 2. I'll lose this hydrogen, this one, and I'll form a carbon-oxygen double bond and aldehyde. Do you break carbon-carbon single bonds? No. I'll slow down, give you time to catch up. Later in the semester, I'll talk about ketchup and mustard and relish too. We'll get a lot of good stuff this semester. And here's my R group. Now, another way of thinking of it is you start with 3 carbons, I better end with 3 carbons. The carbon with the hydroxyl group will be the carbon double bonded to oxygen with a hydrogen. Remember, double bond counts 2 bonds, so this carbon here now has 4 bonds. And that's how you do it. And this is called oxidation of a primary alcohol. I better let you have some fun. And there you go. What would be the product or products of the following reaction? 3 points each. Remember, these are ways we make building blocks to make molecules you use in your daily life. This wasn't an example of the actual molecule, but oxidation is used to make things, other molecules. Thank you, Ignacio. Thank you, Andrew. All right, let's look at this reaction. Question is, give the organic product or products of the following 3 points each. What's different? What's not carbon? What's not? Ooh, oxygen with a hydrogen and a carbon, but alcohol, but we're oxidizing it. And this is a primary alcohol. Here's this carbon right here. So all these are my R group. And when I oxidize it, that's what this O bracket, O close bracket means. I'll lose a hydrogen here and here, and I'll form a carbon oxygen double bond. And I do. And another way of thinking it is, you break carbon-carbon single bonds? No. So I end up with one, start with 1, 2, 3, 4, 5. I better end up with 1, 2, 3, 4, 5. This is my R group. This carbon here is this carbon here, becomes this carbon here, which is double bond to oxygen with a hydrogen. I know there are 4 bonds to carbon. Yep, 4. And that's the molecule you make. And we'll learn these are important molecules you can use in your daily life when we talk about aldehydes. Oh no, I just saw something sad. We're just about out of time today. How sad. But anyways, let me remind you, tonight from 5 to 6:15, I'll have my office hour. If you need help, stop by. Don't forget, this Wednesday, lab is due. Also, this Wednesday, sometime in the afternoon, I will send out the password for the password protected PDF file, which you should be able to download on from D2L tomorrow. And then when I send you the password, you'll put it in, open up the file. You can print it and write on there, and then use your cell phone or scanner to upload it by 11, I think the next morning, Thursday morning, your answers. If you do not have a printer, take a piece of paper, don't forget to write your name on it, and write the problem like 1 or 1A, B, C, if they're multiple part, and your answer. You do not have to rewrite the problem if you don't have a printer. You don't. And with that, I'm right on time to say, Gang gesund. Remember, that means Yiddish being, go in health, even though the pandemic supposedly is done. I still wear my mask to be safe, and I'll get my booster in about 2 weeks, because that'll be 6 months after my last one. With that, I'll say, Gang gesund, goodbye. I stole that from Granny and the Beverly Hillbillies. Bye now.